A second-order homogeneous Cauchy Euler differential equation will have the form seen here. Note the defining characteristic. In each of the terms, we have a constant times a power of x multiplied by a derivative, and the power of x is equal to the order of the derivative in each of those terms. 0th power of x, 0 derivatives. In order to solve a Cauchy Euler homogeneous differential equation, we make a guess. That is y equals x to the m. We substitute that into the differential equation, and it reduces it down to this auxiliary equation. And it's worth emphasizing that we need to be careful with that middle term having the coefficient b minus a. Once you have that auxiliary equation written down, we find its two roots, either by factoring or using the quadratic formula, and then those two roots will fall into one of these three categories. Based upon the category it falls into, we would have a corresponding general solution. So let's go ahead and look at a nice concrete example illustrating how this method works. We will find the general solution of the given second-order homogeneous differential equation. Now, the observation I would like to make, and hopefully you have already made, and that is, at first glance, this does not appear to be a Cauchy Euler differential equation. After all, that defining characteristic isn't satisfied. First power of x, second derivative, 0th power of x, first derivative. We need the power of x and the order of the derivative to match. So one thing that we can always do is we can algebraically manipulate as long as we do the same thing to all terms, or maybe say both sides of the differential equation. So multiplying through everything by x, this becomes x squared y double prime minus 4xy prime equals 0. And once we have it in this form, this is a Cauchy Euler, and it's a homogeneous differential equation. So in order to solve this, we immediately write down the auxiliary equation. And to make this as clear as possible, let me note what those corresponding constant values are. So what we called A is the coefficient or the constant with that y double prime term. Then B is the constant with the y prime term. And because that y term is not present, the c is 0. So our auxiliary equation we write down as am squared plus b minus am plus c equals 0. So in this case, we would have m squared minus 5m equals 0. And once again, just be careful with that coefficient of the m term. Now that we have the auxiliary equation, in this case we easily factor. M times m minus 5 is 0. So we have m is equal to 0 and m2 is equal to 5. So we fall into that first category of having two distinct real roots. Therefore, the general solution is going to be, in this case, c1 times x to the 0 plus c2 x to the 5th. And typically, whenever I'm dealing with this x to the 0 quantity, I will simplify that down to just be 1. So we have c1 plus c2 x to the 5th, providing the general solution of this second-order homogeneous Cauchy Euler equation. And to finish, I would just like to note that there are certainly other types of problems we could encounter besides just second-order homogeneous. So it is very reasonable to encounter, say, a third-order homogeneous differential equation, which is Cauchy Euler. And recall, in that case, our method for solving is we would make that guess y equals x to the m, and then we would algebraically find that auxiliary equation. And the three roots of the auxiliary equation allow us to find those three linearly independent solutions, hence the general solution. Furthermore, we could also have a second order non-homogeneous Cauchy Euler differential equation. Note, if it is a Cauchy Euler differential equation, it is not constant coefficient, which means we are unable to use undetermined coefficients. So in this case, our only choice for finding a particular solution is variation of parameters.